Let's calculate some entropy changes then for a chemical reaction that we are interested in. If we want to calculate the entropy change for that reaction, we're going to do that in a very similar method, or using a very similar method to what we did to calculate enthalpy changes in General Chemistry 1. If you remember, in General Chemistry 1, you should have, anyway, calculated enthalpy changes for reactions using what we called enthalpies of formations, or heats of formation. And those numbers that we used to do that came from an appendix at the back of the book. We're going to do the same thing now, only we're going to do it with entropy values instead. So we're going to use the standard entropies that we talked about in the last video, and we're going to calculate the change in the entropy of a reaction using the exact same equation as before, the sum of the products times their coefficient minus the sum of the reactants times their coefficients. So products minus reactants. And again, we're doing this because this is a state function. The entropy here is a state function. And so it's just where did you end up minus where did you start. That's all we care about. All right, so for example here, in this particular reaction, we're trying to find the change in the entropy value for this reaction given this balanced chemical equation. And so we are going to do the same thing that we saw on the previous slide there. It's just going to be the sum of the products minus the sum of the reactants. So we're going to start here with the products. We're going to take 4 times the number for NO from the table at the back of the book. And so the book that I have here at home is not the same book it's not the same book that you would have at your place, but the numbers should be essentially the same. We're looking at the thermodynamics table. The title of this particular appendix value is this is the standard thermodynamic quantities for select substances at 25 degrees C. It's the name of the table. The book that you're using should be pretty similar. The name of it should be pretty similar. And we want the S naught values. That's what that's called. And it should have joules per mole K as its units. So those are the standard entropy values for different molecules. And so we're going to flip to the nitrogen section, because usually the appendices are arranged in alphabetical order based on the main, so to speak, element in the molecule. So nitrogen monoxide in the gas phase, and the phase does matter, although nitrogen monoxide is only going to be in the gas phase on these tables. That is 210.8. So we have 4 times 210.8 joules per mole K. So that's this one. We're going to add to that 6 times the number for water. And in this particular appendix, I believe water is listed under oxygen. Let me see here. There it is. Okay, so water in the gas phase. You need to be careful about that because it's very easy to get the number for liquid instead. But in the gas phase, the standard entropy of water at 25 degrees C is 188.8. So we have 6 times 188.8 joules per mole K. These units of moles, by the way, are going to go away because I didn't write in there is these also have a unit of moles, because we have 4 moles of NO, 6 moles of water, and so the units of mole are going to go away here. So that is all of our products. Just because I'm going to run out of space here, I'm not going to try to fit the reactants in here. Well, actually, no, I can't. No, I won't be able to fit those in. So I'm just going to go down to the next line here, but if I had the space, I would put it right up here. So these are going to be the reactants down here below. So my reactants, I have 4 times the number for ammonia, ammonia, not ammonium, ammonia. So let's go back to nitrogen here. NH3 in the gas phase has a standard entropy of 192.8 joules per mole K, and again that's 4 moles there. And we will add to that 5 times the number for oxygen. If you remember standard enthalpy values, oxygen, because it's a free element, it's the elemental form of oxygen, it would be 0. It's not going to be the same here with entropy values. The only thing that has 0 entropy would be a pure material and a pure crystal at 0 Kelvin. I say that there are actually a few things, if you look at the table, that actually have negative standard entropy values. But the only situations where that is the case is where you have ions that are in aqueous solution, and so that negative entropy value is actually because it's providing order to the water around it, because it's an aqueous solution. So there are some situations where you do end up with negative entropy values from the table, but that does not mean that the thing itself has negative entropy. It's kind of an artifact of the way that that's calculated. But you'll only see that with things in aqueous phase, with ions in aqueous phase. Anyway, all that being said, 5 times the number for O2 in the gas phase, that is 205.2 joules per mole K. So those are all of our reactants. And so, delta S for the reaction is, oh boy, lots of calculator work here. So 4 times 210.8 plus 6 times 188.8. That answer minus 4 times 192.8 plus 5 times 205.2. The change in the entropy for this reaction is positive 178.8 joules per Kelvin. We can do a little bit of a sanity check here just to make sure that that answer makes sense. If we look at what we have in the reaction, we start with 9 moles of gas and we end with 10 moles of gas. So it makes sense that the entropy goes up. It would make sense that we have a positive entropy. If we started at 10 and went to 9, we would expect to have overall a lowering of the entropy. So our answer does make sense, at least in that sense. All right, so we can calculate the enthalpy change for a reaction. We did that in Gen Chem 1, again, using those numbers from the table. And we can also calculate the entropy change for a reaction, again, using numbers from that table. And we can use the temperature to find the change in the Gibbs free energy. Because remember from previous videos, delta G, the Gibbs free energy, is delta H minus T delta S. So we know how to calculate that using numbers from the table. We know how to calculate that using numbers from the table. If we know the temperature, we can plug all those in and find delta G just using numbers from that table. So let's do that real quickly here. So this is one possible initial step in the formation of acid rain. So we have SO2 reacting with oxygen gas to make SO3 that would eventually go on to make sulfuric acid, nasty stuff, to be in the rain anyway. We want to find delta G at 25 degrees C and to figure out if this reaction is spontaneous. So we are going to find delta H and delta S for these reactions. Sorry, my S looks a little weird there. It's going to be the same thing as before. Products minus reactants. I'm going to shorten this a bit, though, simply because I want to fit them on one line, and I'm not going to have space to put in all the units and everything. So I'm going to leave the units out, but keep in mind that delta H values are going to be in kilojoules per mole, and delta S values are going to be in joules per mole K. So we will have to reconcile the kilojoules and joules in just a minute. But for now, let's just go ahead and find the two values. All right, so we only have one product for our reaction. That's SO3. So if we go to our table and find sulfur, it's going to be towards the back, since S is towards the end of the alphabet. So SO3 in the gas phase has a delta H value of negative 909 that's the wrong one. Negative 395. Something I have to watch out for. These tables are so they're so busy that it can be easy to read the wrong number. So negative 395.7. And that is our only product, and it has a coefficient of 1. So we're just going to leave that as is. So then we're going to subtract from that our reactants. So the SO2 is actually right above it on the table. That's negative 296.8. And then we're going to add to that 1/2 times the number for O2, which if you go over to the oxygen on the table, you will find that it is 0. So it's not actually adding anything to it. So if we go ahead and add those together, negative 395.7, it's going to work out to be plus 296.8, since we're subtracting a negative value. Delta H for this reaction is negative 98.9 kilojoules. And again, the moles go away here because we didn't show it, but we multiplied this by 1 mole, we multiplied this by 1 mole, so that the moles just end up going away. So we're going to do the similar thing down here with entropy values. So SO3 has a standard entropy value of 256.8. And again, I'm just going to leave the units out just for the sake of space. So that's SO3. SO2, right above it on the table, is 248.2. And then we're going to add to that 1/2 times the number for O2, which is 205.2. All right. So again, if we do that math, 256.8 minus, open parentheses, 248.2 plus 1/2 times 205.2. That is going to work out to negative 94 joules per mole. Because again, that, sorry, not per mole, per K. Because the moles go away. Okay. So, we have a delta H. We have a delta S. And we're told that the temperature is 25 degrees C. Do not forget, 25 degrees C. We cannot plug this directly into the equation. It needs to be 298 Kelvin. We need to convert that to Kelvin because it has to match the Kelvin here. So 298 K is our temperature. So then delta G is equal to, let's see, negative 98.9 kilojoules minus 298 Kelvin times negative 94, we're going to do 94 times 10 to the negative 3 kilojoules per Kelvin. So again, the reason I did this here is because I needed to get these two in the same unit. Alternatively, if you wanted to leave this as just negative 94, we could have made this negative 98.9 times 10 to the third joules. It would end up being the same thing. But I'm going to go ahead and stick with having kilojoules for both of them. So if I do that math, 98.9, negative 98.9 minus 298 times negative 94 times 10 to the negative 3. That is going to give me delta G is equal to negative 70.9 kilojoules. So if I had stuck with joules instead of kilojoules, I would have ended up with negative, what would that be, 70,900, I guess, kilojoules, or joules. So, is this spontaneous? Yes, it is spontaneous. And we know this because it is a negative delta G value. Because remember, negative delta G values are spontaneous. Positive delta G values are non-spontaneous. All right. So you might have noticed that was a lot of work. That took a really long time. We had to get all the numbers for the delta H values for everything in the reaction. We had to get all the delta S values for everything in the reaction. We had to add them all together, multiplying by coefficients, put those into the other equation. And that was with a simple reaction. Like that reaction only had 3 things in it. What if we have a reaction that's more complicated? 4 or 5 things involved in the reaction. It would take forever. There must be a better way. And you might have noticed getting numbers, if you actually had your book out and you were actually getting the numbers and working along, you might have noticed that there is actually a third column in that thermodynamics appendix that contains standard Gibbs free energy values. And so there is, in fact, a better way. You do not have to get all the numbers for delta H and all the numbers for delta S and do all those calculations and then plug it into a separate equation. Instead, scientists in the past have been very kind to us, and they have actually done all those types of calculations for us and worked out standard Gibbs free energy values. And we can do the same kind of equation, but with Gibbs free energy values instead of doing 2, essentially, with an extra equation added on as well. So in the next video, because I know this one's been a little bit long at this point, next video we will work through a problem using the standard Gibbs free energy values.